All right, ladies and gentlemen, I want you to title your notes Implicit Differentiation. Now, this topic is easy-ish in practice, the actual act of doing it, but the conceptual understanding of why we do it can be a little bit challenging, and I want to try to tackle that now. So first of all, have I ever asked you to find the derivative of something like this? Well, the answer is no. Look at how there's x's and y's in the equation, especially this ln y right here. You might say, hey, Ms. Sorensen, we've done something like y equals 2x squared, and there's a y here and an x here, and you're totally right. Basically, we took the derivative of y, which is dy dx, or you could say y prime, and we took the derivative of this. This is 4x. But did you know that there's something invisible right here and something invisible right here? And those invisible things are essentially equal to 1. Well, let me see if we can go back to this. Let's go back to our ln x equals y plus 2x plus ln y. In the problem like this, we know that the derivative of ln x is 1 over x. We know that the derivative of y is dy dx. We know the derivative of 2x is 2. And this one's a little bit funny. And my hint to you is that there is a hidden chain rule. The derivative of ln y is actually going to be 1 over y times dy dx. Essentially, we're taking the derivative of this and keeping our y, our inside, and then we're taking the derivative of our inside. That's like the chain rule, taking the derivative of our baby. What's the derivative of y? Well, like here, it's dy dx. All right, so let's go back to this problem right here. What do you think is missing? If I take the derivative of y, I get dy dx. But you take the derivative of the inside function, what's the derivative of y? Well, that would be 1. Similarly, what's the derivative of 2x squared? Well, that's 4x. But then what's the derivative of our inside function? Well, that's dx dx, which is equal to 1. So this is really kind of confusing right now, but I promise you that it will get more clear as we do more problems. This problem right here isn't quite solved. We could certainly solve for dy dx, but that's not the purpose of this slide. The purpose was to introduce this hidden chain rule. So that problem's not completely solved, but that's all right. We got our point across. Let's actually do a problem now. So what we're going to do here, and instead of using dy dx, let's go ahead and use y prime. This dy dx and y prime are exactly the same thing. So let's call this my first, and let's call this my second. So I'm going to take the derivative of everything here. So what's the derivative of my first? That's 3 times my second, which is y, plus what's the derivative of my second? Well, what's the derivative of y? Well, it's y prime, times my first, which is 3x. Okay, now I'm going to go ahead and I'm going to do this. So I'm going to do plus 8y, and then I have to take the derivative of my inside, which is y prime. And then what's the derivative of 10? It is 0. Now you might say to me, Ms. Sorensen, why isn't there an x prime here? Well, the answer is that anytime that we are taking the derivative of a y, we have to tack in that y prime after taking the derivative. But as you can see here, in an example where we did the derivative of 2x squared, we got 4x and then a dx dx. But that doesn't matter. That disappears. That's 1. So that doesn't need to happen. All right. So now this is asking us to solve for dy dx. So what I'm going to do is I'm going to keep all the y primes on the left, and I'm going to get everything else on the right. y. So this disappears and I'm left with y prime 3x plus 8y y prime equals negative 3y. Next thing I'm going to do is I'm going to pull out a y prime. So that gives me a 3x plus 8y equals negative 3y. And since I'm solving for y prime, which is the same thing as dy dx, I'm just going to divide by 3x plus 8y, 3x plus 8y. This cancels and this cancels, and I get y prime equals a negative 3y over 3x plus 8y. And that's my answer. If you want to, instead of writing y prime, you can write dy dx. I just find it much easier to deal with y primes in my problem. All right, we have completely solved the first one. All right. Why do we do implicit differentiation? Well, we do it when an applied problem involves an equation not in explicit form. Implicit differentiation is used to locate extrema, write tangent lines, and find rates of change. So we'll certainly be doing tons of applications in our next unit on this. Just know that this right here, that is in an explicit form where y is solved for y equals. But in a problem like 2x plus 4y ln x equals 2, this is implicit. We have not solved for y. But we're learning that we can still take the derivative of it and solve for y prime, or dy dx. All right, what is the process? You're going to differentiate both sides with respect to x. You're going to collect all like terms, all the dy dx's, or you can call that y prime, on the same side, and you're going to put everything else on the other side. Factor out the dy dx, or the y prime, and solve for dy dx, or y prime. Note, anytime you are taking the derivative of a y, you have to put in y prime. So for example, if you have 2x plus y squared equals 5, when I take the derivative of this, I just write 2. When I take the derivative of this, I write 2y, but then I put a y prime. Take the derivative of this, I get 0. So my note to you is when you're taking the derivative of y, make sure you put a y prime after taking the derivative, after doing the derivative process. Okay? And you might be saying, Ms. Sorensen, why not here? Why not here? Why wouldn't you have that? Well, remember, that's dx, derivative of x with respect to x. And so that disappears. Versus here, we've got a dy dx, and that does not disappear. You don't need to know that. You just need to know that whenever you're taking the derivative process with y, like you got the 2y here, just make sure you tack on a y prime. All right, let's get some examples going here. Okay, find dy dx, or you can think about that as y prime, if we've got this. Let's call this our first. Let's call this our second. We'll call this our first. We'll call this our second. Actually, that's not really a first or a second at all, is it? Now I'm thinking, I got deja vu here. We actually have already done this problem. I'm not going to redo this video because we're 9 minutes in, so we are going to move ahead, and you're just going to giggle at me. All right, here's some more practice. We've not done this problem. So given x squared plus xy plus y squared, find dy dx, or find y prime. Okay, derivative of this is 2x. Now let's do product rule. So this is going to be my first times my second. Derivative of my first is 1 times my second plus derivative of my second. Derivative of this is y prime. Or you can think of it as 1 and then y prime times my first. Plus, take the derivative of this, that's 2y. Don't forget to tack on your y prime. And then the derivative of a constant is 0. Now you might be saying, Ms. Sorensen, why didn't you put a y prime here? Well, that's because this is the derivative of my first times my second. I'm not taking the derivative here, I'm just multiplying it by the second value. All right, so now I'm going to get these two things, minus 1, that's just going to be a minus y, right? 1 times y is minus y. 1 times y is y, and I'm subtracting y. So now I'm going to subtract 2x minus y from both sides. Gone, gone. I get y prime x plus 2y y prime equals a negative 2x minus y. Okay, factor out my y prime. I get an x plus 2y equals negative 2x minus y. Divide by x plus 2y. And I have my answer, because these two things cancel. So I'm left with y prime, or dy dx, equal to negative 2x minus y over x plus 2y. Yahoo! What a joy. All right, let's do another one. Derivative of x squared is 2x minus 8 plus 2y, and then I've got to add on my y prime, equals 0. Let's get everything else on the other side. Gone, 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 gone. 2y y prime equals minus 2x plus 8. Pull out a y prime, I get 2y. Divide by 2y. Cancels. And I'm left with a y prime equals negative 2x plus 8 all over 2y. Are you starting to get the hang of this? Like I said, conceptually you're like, whoa, what is going on? But mathematically it ends up being okay. All right, I'm going to pause this video and then we're going to have a part 2. It is important that we get lots of practice with this.